Hello everyone. In today's module, we will continue our discussion of functions. We will look at some examples of functions. We will talk about how to graph functions. You can graph them using Wolfram Alpha, which is simply going to any browser of your choice, typing in Wolfram Alpha and going and plotting in what do you want to calculate or know about. We are not going to get into that discussion. What we will be talking about here is to how to plot functions by hand, which is a very useful trick. And as you will see, it also gives you intuition into a given problem. And thirdly, we are going to look at some generic properties of functions. So last module, we ended by talking about a list of functions, and I asked you to think about the number of parameters in that function. So hopefully you did that. If not, let's look at it together. So a straight line through the origin is, so in general, we are talking about f of x, which is y is equal to f of x, and this, what we are trying to understand is what is the form of this f. So for a straight line through the origin, this is mx, y is equal to mx. There is only one parameter, and as we will see in a bit, this line looks something like this. You have x and a y, and it looks something like that. A generic straight line needs two parameters. It will be mx plus c, because you also need to specify the intercept of this line in this plot over here. So this had one parameter, this had two parameters. A Gaussian in the most generic case would be given by h multiplied by e to the power minus x minus some center a whole square by 2 sigma square. So over here you can see that's 2 sigma to the power 2. You have a parameter h, you have a parameter sigma, and you have a parameter a. So you have a total of 3 parameters. So sometimes a Gaussian is used as a probability density, in which case you have a constraint on what these parameters should be, so it might come down to 2, but this is a general case of a Gaussian function. An exponential is a curve or a function that shows up in a lot of physical chemistry, and in the most generic case, it is given by e to the power minus x minus a by sigma multiplied by some height h. So it's very similar to a Gaussian, but not all the way. And again, you have 3 parameters here, h, a, and sigma. So the number of parameters in this case is again 3. A quadratic is ax squared plus bx plus c. Easy to see that the number of parameters is again 3. It does not mean every function in the world has 3 parameters. A generic case, a generalization of a quadratic, is a power series, not with n terms. Let's actually call it a power series with power n. This is defined as series that look like a naught plus a1x plus a2x squared till all the way an xn. So these subscripts here, 0, 1, 2, a0, a1, a2, an, these are different parameters. And a precise way of writing this is to say summation over ai x to the power I, where I goes all the way from 0 to n. So here you can see you have n plus 1 parameters. So these are some examples of functions which show up in a lot of chemistry, physical chemistry, and variety of related topics. And what all of these are doing is to take a value of x, and given it, all of them, the common property is that they take a certain value of x from domain D, and we will talk about what does this domain exactly mean. So x could be any integer, for example, then the domain would be the set of all integers. X could be all real valued numbers, then the domain D would be the set of all real value numbers. Operate on this using the rule f. So you take a certain value of x from a domain D, you operate on it using the rule f, and then you obtain value y. So these are the 3 key steps in functions. So here, for example, if x is equal to 1, you operate on it for a given value of m. You need to know what is m, and then you get a certain value of y. And this is the key in Plotting functions. Of course, I did not talk about trigonometric functions, sine of x, cosine of x. I did not talk about sigmoidal functions. There are lots and lots of functions, and you can go up and look up the Wikipedia page on functions, and you'll see basically there is an infinitely many number of functions. So how do we graph these functions? Like I said, the easiest way to do it is to go to Wolfram Alpha and do it. But what if you're stuck on an island, on a desert island, or what if internet is gone? Or often it's not just these excuses such as you being in a place without internet that you need to graph functions. It can actually be very useful when you're trying to come up with a theory or trying to come up with a model for a system. As you work through any science course, the ability to graph functions on your own is extremely useful. At least that's what I have found in my career. So let's look at examples of graphing functions. Let's say we want to graph the function y is equal to x squared over domain. And now I will specify the domain -2 less than equal to x less than equal to 2. So how do we do this? Let's make a table. That's the simplest way of doing this. So let's make a table where we will write down certain values of x and we will write down the corresponding values of y. So here we will write down x and here we will write down y is equal to x squared. So if x is equal to -2, y is equal to x squared would be 4. X is equal to -1, y is equal to x squared would be 1. X is equal to 0, it will be 0. X is equal to 1, it will be 1. X is equal to 2, it will be 4. So we have a sense of how things are going to look like. So let's draw our axes. And let's call this one as x, let's call this one as y. And let's make some, and this has to be approximate. This is not a very accurate plot, but it will at least give you a flavor of what's going on. So this is 0, this is 1, this is 2, this is 3, this is -1, this is -2. We really don't want to go to 3 because the domain is in the -2. And over here on the y-axis, we will again plot 0, 1, 2, 3, 4. So 1, 2, 3, 4, 5. So we know that this at x is equal to -2, it takes the value 4. So it's around here. At x is equal to -1, it takes the value 1. So around here. At x is equal to 0, it takes the value 0. So around here. Again, x is equal to 1, it takes the value 1. X is equal to 2, it takes the value 4. Here we have 5 plots, and all we need to do is to draw a curve, approximate curve that goes to them. And bingo, we have the function y is equal to x squared. I will draw a star here and ask you to go check on Wolfram Alpha as to how this looks like, and you will see it's remarkably simple. So this is the basic way of plotting a function y is equal to x squared. What we don't know in this one is what happens in between these two blue points, right? Like, why could it not be like this? Why could it not be like this? That is wrong, and the way to answer that will come through calculus, and we get there later. This function, we will be able to tell from calculus, must have only one minimum, which is right over here. And these are advanced topics which we will get to. It's not that advanced. In a few modules, you would have mastered these things. So this is how we plotted y is equal to x squared. We can do a similar one. Let's plot y is equal to x cubed, which is a bit more fun. For y is equal to x cubed, let's do the same thing. We will make a table, and we will talk about certain values of x. We will talk about certain corresponding values of y. So let's do the same thing, -3, -2, -1, 0, 1, 2, 3. And here I have changed my domain and I want to plot it over. So we know this is going to be -27. This is going to be -8. This is going to be -1, 0, 1, 8, 27. And if you go and plot these values, what you will see is, so at 0, it looks like 0, 0. So And I told you last time to always label your axis. So let's do that. Let's plot a bunch of approximate numbers over here. Let's call this 5, 10, 25, -5, minus, actually we will run out of numbers like that. On X, we don't want to, so when you plot these numbers, you have to be conscious of the range that you have. So over here, we can see the X range is small. It goes from 1 to 3, and over here, -1, -2, -3, while the Y range is much larger. It goes from 0 to 27. So we need bigger numbers for Y. So let's call this 5, 10, actually, even that's not going to do it. So let's go with 10, 20, 30, -10, -20, -30. And now you can see that at 0, it's 0, 0. At 1, it's quite small. If this is 10, it's maybe somewhere around here. At 2, however, it becomes quite large, almost at 8, almost at 10. In fact, 8 is the value. And at 3, it goes up all the way to 27. Over here, at -1, again, it is very small, so somewhere around here. At -2, it is somewhere around here, so it's -8. At -3, it drops down all the way to -27. And if you join this curve, these bunch of dots, you will get a curve that looks like this. That is y is equal to x cubed. And again, I would like you to go and look at Wolfram alpha. So this, in a nutshell, is your first introduction to graphing functions. Once we do some calculus, we will come back to these functions and talk about minimum and maximum and extremum and all kinds of wonderful properties. So we did our graphs, and I want to mention some very generic properties of functions without getting into too much abstraction. So last time we mentioned that a function is y is equal to f of x, where x is in some domain D. And the values y that you get are in some range R. We did not really talk about examples of this domain and range. So this could be multidimensional. The domain could be multidimensional, which means you could look at pairs of numbers, you could look at triplets of numbers, you can look at all sorts of abstract properties, and same thing for the range R. They could be multidimensional. But we will focus, however, so for example, they could be complex valued numbers, and there is another module on complex numbers, you can go and look that up. We will, however, focus on real valued functions where both the domain and the range are real numbers, where D, R are real numbers. So that's the first property of function that I wanted to mention. I want to stop this module before 15 minutes, and we are about to get there. So the next time what we are going to talk about is some more properties of functions. For example, what does it mean for function to be even, odd, and symmetric, and some other properties in next module. With that, thank you very much.